Hi, welcome to Chem 6161. Today we will talk about the Aldol reaction. One example of the Aldol reaction is what I wrote in the slide. We have a ketone plus an aldehyde, we use a base, and what we get is a 1-keto-free hydroxy compound. Okay, the basic mechanism is first we do an ion of the ketone with LDA, we remove the alpha proton to the carbonyl group, and then this is attacking the aldehyde. And normally this is by acrylate to form this final compound. The importance of this is that if we check the transition state, what we have is 1, 2, 3, 4, 5, 6, a 6-member transition state that we can grow it like a chair transition state. Okay? And what we can do is if we draw this transition state as a chair, we have this possibility. Where the lithium is here, we put the aldehyde here, and then in this place we put the anode. In this case, we have to generate an enolate. For example, we can generate this trans enolate, and what we'll have is this compound, this transition state. Okay, what is important of this transition state? This position, that is the alpha position of the enolate, will be determined by which type of enolate we are doing. For example, in this case, I put that we have the trans enolate, and because it's trans, this methyl has to be in equatorial position. But this position is fixed by the enolate. The next position that we have to take a look is this position, the position of the benzaldehyde or the aldehyde. Okay, when we saw this thing, what we have to consider is to put the bigger group, in this case the phenyl, in the equatorial position. While this hydrogen is in the axial. Once we have this transition state, the only that we need to do is to grow it in the correct form, and what we get is this is coming to us, and the next one, basically we are forming this bond. What we have is that the edge is inside. Okay? This is the transition state, the chair transition state for this compound. Then normally in all the lectures, in all the exercise, what I will give to you is which enolate we are using. Okay? In the lecture you can find some examples of enolates that we can form selectively using, for example, boron reagents, or when we have very big substituents in some part of the ketone. Please take a look. But as I told you, this, in 100% of the cases, I will give you the enolate that we will use. Okay? Easy, we draw the transition state. How I draw the transition state is, I put always the lithium in this position, or the metal in this position, okay, the chelate in this position, and then I draw the enolate on the plane of the slide, and the benzaldehyde that is coming in front. Okay? You can do it in another way, all could work. The only that I recommend you is to always use the same way. Okay? One way that you feel comfortable with. Okay, but we can complicate a little bit this. Okay, what happens if we are using a chiral aldehyde like we saw in the last lecture, in the Felkinan lecture? Well, what we will do is to put an example. What happens if we do exactly the same reaction, but this time we use this aldehyde? Okay? This aldehyde is chiral. That means that what we will get is this compound. Sorry. Okay, we are generating these two stereocenters, and this stereocenter will be the same because it's a chiral one that we used from the beginning. Okay, obviously now the products that we will obtain are diastereomers, and because this is chiral, what we will have is that one of them will be favored over the other. How we do it? We have two different ways to do it. The first one is apply what we learned in the Felkinan. Okay, in the Felkinan, we know that if we attack a nucleophile over an aldehyde, we know which phase will be favored. That means we draw it. In this case, what we have is this. Okay, I put the phenyl here. If I saw from here, what I saw is the methyl in this position and the hydrogen in this position. If I do the rotation, I put the right rotation directly, okay, in order to save time. Okay, this is the first rotation where the nucleophile will attack from this part. Okay, then what we do is exactly the same that we did before. We draw the transition state. Okay, I put the lithium here. Here I will put the enolate, that will be the same as before. Okay, the trans enolate. And here I will put the aldehyde. And then I have to check if this is the right phase. If the attack takes place by the right phase. Again, when I draw this transition state, I put the lithium here, I draw the enolate trans because it's trans at the beginning, okay? And what I do is put the enolate on the plane of the slide, and then the benzaldehyde, the aldehyde, is approaching from in front. Then, if I do this, the phase that I am attacking is the same phase that is the favored one by the Felkinan. Okay? If it is not true, that means the phase that I am attacking is just the opposite, what I have to do is simply draw the other transition state. That will be basically put the lithium here. Okay. Here will be the enolate. Here will be the aldehyde. And if you take a look in this drawing, I am drawing in this drawing, the phase that is attacking is just the opposite that in this drawing. Okay? Basically, these are the two pseudo-enantiomer transition states. One is the mirror image of the other if we don't consider the stereocenter of the aldehyde. Okay? Right? Again, I draw it in the same way. I draw the lithium in one of these positions. Okay, and then the enolate is on the plane of the slide, and the aldehyde is approaching from in front. Of course, when I draw this is the wrong phase of the aldehyde, and this is the right phase that, if I draw it in the correct way, what I get is that the OH is coming to me. Okay, I am translating this transition state to the compound. The metal is going inside. This metal is going inside. Okay? This is one method. We apply the Felking-An to the chiral aldehyde. In this case, it's the normal Felking-An, only considering steric factors. I find which phase will receive the attack, and then I draw the two possible transition states, and I took the transition state where the attack is happening in the correct phase. Right? Okay. Second method to do it. In the second method, what I do directly is draw the transition state. I put the lithium here. I always draw in the same way. This is the enolate, and then here will be the aldehyde, and now I will draw the chiral one here. Okay? Okay, this is the chiral center. And what I do is to put the phenyl as far as possible of the enolate. What I get is, in this case, I rotate this. If I put the phenyl in this direction, what I get is hydrogen direction and the metal down. I will try to draw it a little bit better. Okay, if you see it, I put the phenyl far away, the metal is going down, and the hydrogen is going inside in this case. If I draw the other possible transition state, okay, I do exactly the same. And here again, I draw the phenyl as far away as possible. That means if I draw the phenyl as far away as possible, that means the phenyl is here is the hydrogen, and here is the methyl. Please, if you don't see how I rotate this chiral center, or this chiral center, please check it in the, how to say, check it using molecular models. Okay, and then I analyze the two different transition states. In this case, I'll put the phenyl as far as possible, and the hydrogen is going inside. Okay, that means the crash is between this hydrogen and the enolate. While here, when I put the phenyl as far away as possible of the enolate, what is facing the enolate is the methyl. Which will be more stable? This will be more stable. That means that this will be the transition state, and if we grow it, will give us exactly the same result as before. Okay? Basically, what I do here is I grow the transition state, and then I check this, the alpha atom of the aldehyde, putting the big group as far as possible of the enolate. Okay? And this will be the Felkin product. Why I explain this method? Okay, because this method must be applied when we are using a cis enolate. Okay? Why? Well, what happens if instead of a trans enolate we have a cis enolate? That means that instead to have this enolate we have this enolate. Okay? What happens? Well, we draw exactly the same drawing. Okay, lithium here, oxygen, oops, here will be the enolate with the metal down now, the hydrogen in this direction. And here we draw exactly the same aldehyde, and here the substituent. And what is happening now? What is happening now is that if you take a look, okay, this position and this position is a sympentane interaction. And we know that this destabilizes a lot any transition state if we have a cis-pentane interaction. For this reason, when we have a cis enolate, what we have to do is minimize this sympentane interaction. That means in the alpha proton we have to put the lower substituent, the smaller substituent, in the sympentane position. That means in this case we have to put the hydrogen here. If the hydrogen is here, the phenyl is inside and the methyl is outside. Okay? Why? Because we have to minimize the interaction between this substituent and the methyl. If we draw the opposite transition state, okay, what I get is exactly the same here, the metal down, here the hydrogen, here the R, and then here I draw exactly the same aldehyde. And now again, what I do is I have to put here the smaller substituent. If I put the smaller substituent here, inside is coming the methyl and outside is coming the phenyl. Okay? And now we analyze both. In this case, the phenyl is crashing the enolate, while in this case, the methyl is crashing the enolate. That means that this will be the more stable. if I took this, the only that I need is to grow it. That basically is okay. OH inside. Methyl inside. Okay? This will be the final configuration of the major diastereomer. Okay? Why? Because in the case of the cis enolates, I have to consider that the major issue is the syn-pentane interaction. I have to minimize it. I have to put the smaller substituent in the syn-pentane position. Okay? That's a big difference between cis and trans enolates. And that's all. Please do the exercise. What I recommend is that you do all the exercise and be confident growing these both structures, these Chiral structures, okay? And my recommendation is that if you don't see any of the rotations or the 3D of these models, please use molecular models, okay? At the beginning will be a very good help. Okay? Good. Then, the last one that I will explain in the Aldol reaction is what happens if we are using a chiral auxiliary. Okay? For example, I will focus in the Evans auxiliary. Means, for example, we are having this reaction. Okay? This is a typical Evans auxiliary. And we react with Benzaldehyde. What will happen? Well, the first thing is that when we are doing this, we have to generate the enolate. Normally, we can use LDA, but normally is a boron, okay? And triethylamine in order to make the ion. And a good thing using the Evans auxiliaries is that, of course, we can have, oops, we can have both both enolates, the cis and trans enolate, but because of the structure of the chiral auxiliary, this, when we have the trans enolate, this is crashing with the substituent of the Evans auxiliary, destabilizing this enolate. That means that the only enolate that we form, or at least the major one, will be always the trans enolate. Sorry, the cis enolate, not the trans. Okay, will be this. And then the only that we need to do is to grow the cyclic transition state like we did before. Okay, basically, I put the boron here. Here I will put the enolate, that in this case has to be cis enolate. Okay.